Please title these notes Graphs 9 Notes, Absolute Extrema, and write today's date. By the end of this lesson, you should be able to find the x and y coordinates for the absolute maximum or the absolute minimum of a function. Let's start off with a few definitions. An extremum, so the plural is extrema, all that means is it's just a generic term for a maximum or minimum. So when a problem says find all extrema, it's just saying find all maximums and minimums, or maxima and minima actually, if you want to use the Latin plural. And so there are two different types of maxima and minima. A relative, also called a local maximum, is the highest point of the points near it. So when we drew our little symbol for it, we're just looking at the points right near it. It goes up, stops increasing, starts decreasing. We don't know what's going on over here. Maybe there's a higher point over here, maybe there's a higher point over here, we don't know. A relative maximum is just looking right in this little tiny area. Likewise, a relative or local minimum is the lowest point of the points near it. However, there is a different type of maximum and minimum. Sometimes we don't just want to know what's the relative, what point is the lowest or the highest of the ones near it. Sometimes we want to know overall on the entire graph, what's the highest point, what's the lowest point. This is really useful for things like what's the highest amount of profit we can make as a company or something like that. That is called the absolute maximum or minimum. So the absolute maximum is the highest point on the entire graph, while the absolute minimum is the lowest. The absolute minimum and maximum may be at a relative minimum and maximum, but they don't have to be. So for example, in this case, let's say our graph starts up here at this point, it comes down, it goes back up again, it goes down, stops here. So here we have a relative minimum, but the absolute minimum is actually here. It's not what we would think of as a relative minimum because it doesn't change from decreasing to increasing right here. But it is the lowest point, so it's the absolute minimum. And likewise, here's where we have a relative maximum. But this is actually the highest point on the graph. It's the absolute maximum. So one of the really key things to be aware of is that these may occur at endpoints. I'm actually going to go and star this because it's a really important thing to be aware of. Now, they don't have to occur at endpoints. So for example, we could have a curve that looked like this. Here we have a relative maximum. It's also the absolute maximum. This is the absolute highest point on the graph. So let's look at how to find absolute extrema. First thing you're going to do is find all relative maximum. And I'll do the instructions for minimum in purple. Whichever one you're looking for. Then the second thing is we find the value of f of x for each relative maximum or minimum. And also for the endpoints. Again, this is something that's extremely, extremely, extremely important. Very often, the absolute maximum is going to occur at the endpoints. You have to check there as well. So then we're going to pick the largest, or if you're doing minimum, smallest. Value, actually I should say or smallest. And then the final step is often overlooked. It's probably one of the most common errors on the test. Read the question carefully. To see if it wants the value for x, the value for f of x, or the coordinate point. I guarantee you, if you have a question that's asking for the value of f of x, one of the answer choices is going to be the correct answer to a different question. Let's start out finding the absolute extrema if we have a graph of the function that we're interested in. Finding extrema given f of x. So let's find the coordinates of the absolute value, the absolute maximum of f of x. And let's have one right here that looks like this. And a second one over here that looks like this. You can go ahead and just sketch these on the paper in your notes. I just did them on graph paper to make sure that there was no confusion for you because of my graphs being unclear. So notice that both of these are f of x. This is the graph that we're interested in. So when we're looking for the absolute maximum, we're just looking for the highest point on the graph. So here, right here at this endpoint, we see the point -4, 2. That's our absolute maximum. Here we see the highest point here is also at a relative maximum. That's the point 3, 3. That's a little arrow. And there's our absolute maximum. That's it. If you have graphs of f of x, there are a couple of sort of exceptions or kind of weird little graphs. So let's put that here. Let's say this was part B. These are exceptions.
Let's say we have a graph that looks like this. This is x, this is f of x.
And occasionally you'll see something that looks like this. Where it simply continues on forever, and where we have a vertical asymptote here where this goes down forever and doesn't really stop. And if we're asking for the absolute maximum just overall in general, it keeps going forever. There's no point where it actually stops. What we would have to have here is we would have to be asked for the absolute maximum within, let's say, this interval, where we could see that there's a particular stopping point or a particular stopping point. We also have occasionally graphs that look like this. Where instead of being closed circles here, they're open circles. If they're open circles at the highest point, that means there's actually no absolute maximum. Basically, the open circle means that this curve is getting closer and closer and closer and closer and closer to this point, but it never quite gets there, but it keeps getting infinitely close. If it's getting infinitely close, there's no actual number that we can just nail down and say, okay, that's the absolute maximum. However, there is an absolute minimum right there. It's a closed point, that's okay. If, on the other hand, we have something like this, where there's a discontinuity, and this point, instead of being down here like we'd expected, is up here, this is the highest point, so it is the absolute maximum. It just makes our brain hurt because it's not where we think it should be. In this case, there is no absolute minimum, because the point that we would think of being the absolute minimum isn't there, it's been moved. This is why it's really, really, really important that we have functions that are continuous before we do anything involving calculus. If we have this discontinuity, it just messes things up completely. Finding the absolute maximum from an equation is a little bit more involved. However, it's really very similar to finding a relative maximum. There's just one extra step. So finding absolute extrema from equations. This will be very similar to finding relative extrema, but you need to check the y-coordinates of the relative extrema and the endpoints. Once you do that, you can compare the y-coordinates to see which is actually the most extreme value. So let's do a problem. Find the absolute maximum of f of x equals negative 3x to the fifth plus 5x cubed. Now we know we're talking about any maximum, we're talking about f of x, so that means our answer line is going to be increasing, decreasing. And if we're working with an equation, that means that we have to be working with a plus minus line. Plus minus, the f prime is what translates into f of x being increasing, decreasing. F prime of x, check. So now I need f prime. We know that f of x equals negative 3x to the fifth plus 5x cubed. So that means f prime of x is going to be negative 15x to the fourth plus 15x squared. We can factor. Let's factor out negative 15x squared. So that's going to give us x squared right there. We factored out a negative, so this is a minus 1. We can factor that further. X plus 1, x minus 1. If you factored it with negative x squared plus 1 and positive 15x squared, you'll still get the same answer. You'll just have everything reversed from what I'm doing here. Okay, negative 15x squared equals 0 when x equals 0. X plus 1 equals 0 when x equals negative 1. X minus 1 equals 0 when x equals positive 1. We can put those up on the chart. And now if we have a very negative number, this negative 15 is always negative. X squared is always positive. Negative 2 plus 1 is negative. Negative 2 minus 1 is negative. That's 1, 2, 3 negatives. So this is negative overall. Between negative 1 and 0, negative 15 is always negative. X squared is always positive. Negative, let's say 0.5 plus 1 is going to be positive. Negative 0.5 minus 1 is negative. That's positive overall. Between 0 and 1, negative 15 is negative. X squared is positive. Positive 0.5 plus 1 is positive. Positive 0.5 minus 1 is negative. Still positive overall. Greater than 1, we've still got our negative and our positive right here. 2 plus 1 is positive. 2 minus 1 is positive. Negative overall. Let's translate that. Decreasing, increasing, increasing, decreasing. Okay, so we're looking for the absolute maximum of f of x. So looking here, we have something for f of x that comes down like this, goes up, and then comes down like this. And I actually forgot part of the problem. This should be on the interval -2 to 3. Otherwise, we can't really find an absolute maximum. So this is -2, this is 3. Okay, my bad. So, if our function goes like this, then we have a potential absolute maximum right here. That's the relative maximum. But we also could have a potential absolute maximum right here. Maybe what happens is that it starts off, f of x starts off really high, comes down, goes up, comes down. So the actual highest point is over on this endpoint here. So what we have to do now is we need to check, let's do this in blue, we're going to find f of -2, which is one potential absolute maximum. We're going to find f of 1, and we're going to compare them to see which is really the largest. It's kind of as if these are in a little boasting match. I'm the maximum, I'm the maximum. No, well, let's check and see. So, we have a possible absolute maximum at x equals -2 or x equals 1. So let's find them. F of -2. Here's our equation. -3 times -2 to the 5th plus 5 times -2 cubed. It's -3 times -32 plus 5 times -8. So this is 96 minus 40. It's 56. compared to f of 1, whoops, there we go, which is negative 3 times 1 to the 5th plus 5 times 1 cubed. So clearly this is larger. The absolute maximum of f of x on the interval negative 2 to 3 is 56 when x equals negative 2, because f of negative 2 is greater than f of 1, and all other points are less than one of these. Let's do another one of these for practice. Find the coordinates. So that's x and y of the absolute minimum of f of x equals 3x times e to the negative x on the interval 0 to 2. Okay, minimum f of x. That means it's f of x, it's an increasing, decreasing line. Working with equations, so we translate that to plus minus, and the translation is f prime of x. So that means we need f prime. These are being multiplied together, so we're going to use the product rule. Derivative of the first times the second plus the first times the derivative of the second remember, this has to have the chain rule because it's not just an x up there. Okay, we can do some factoring here. This factors out to be 1. So x left over. That never happens. X equals 1. So we can make our sign chart. Over on this side, this is always positive. Let's say we've got 0. 1 minus 0 is also positive. Over on this side, 3e to the negative x is always positive. 1 minus, let's say 2, that's going to be negative, so it's negative overall. Translating that, we've got increasing and we've got decreasing. So notice there's a relative maximum here. We're asking for the absolute minimum. And I did it again. I need to stop at 0 and stop at 2, because otherwise we can't find it. But I did put it in the problem this time, at least. So what this means is it means that we have potential absolute minima right here and right here, because that's where f of x starts increasing or stops decreasing. So now we have to find f of 0 and f of 2 and compare them. 3 times 0 times e to the 0, well, this is all multiplied together and one of them is 0. So f of 0 clearly equals 0. And then for f of 2, that's 3 times 2 times e to the negative second power. So if we work with that negative exponent, 3 times 2 is 6. We don't know exactly what this value is without a calculator, but we do know that this is definitely positive. That is definitely 0. 0 is less than all positive numbers, so this is smaller. So this means the coordinates of the absolute minimum of f of x on the interval 0 to 2 are 0, 0, because f of 0 is less than f of 2, and all other values are bigger than these. We can also find absolute extrema from a graph of f prime. Let's say we have a little graph right here. But to be able to do this, though, we first have to be able to find the value of any value of f of x if we have a graph of f prime of x and an initial condition. So first, let's go ahead and refresh that. Remember, an initial condition is just something that we're told, like f of 2 equals 3, or something like that. So let's do an example. F prime of x is graphed at right. If f of 2 equals 3, which it should be 1, this right here should be A, find f of 5. So here's our little graph right here. The key thing to remember is the fundamental theorem of calculus. We know f of 2, we want to find f of 5. We can use the fundamental theorem of calculus to relate those. The integral from 2 to 5 of f prime of x dx is going to equal f of 5, which we want to know, minus f of 2, which we actually know. Remember, with the bounds, left on bottom, right on top. So 2 is on the left, so it goes on the bottom. 5 is on the right, it goes on the top. So now the thing is that we know that the integral from 2 to 5 is the signed area of f prime. So we can hop right over here and say, okay, from 2 to 5, what is this signed area right here? And this is a triangle, so it's -1 height times 1 over 2, or negative 0.5. And this is 2 by 2 divided by 2, or 2. So this is going to be -0.5 plus 2. F of 5 we want to know, and f of 2 we're told is 3. So if we add this up, this is 1.5. Add 3 to both sides. We can also do the same thing if we wanted to find, say, oops, this is part B, find f of -1. Other than that, the problem's the same. Well, we know the integral from -1 to 2 because we know f of 2, and we want to know f of -1 of f prime of x is f of 2, which we know, minus f of -1, which is what we want to know. And again, we know that the area from -1 to 2, right here, is going to give us this integral. And so what we have here, actually with this one, we can just count blocks. 1, 2, these are each a half, so that's 3, 3.5. F of 2, we're told is 3. F of -1 we want to know. So there's a minus sign there, so let's add f of -1 to both sides. Subtract 3.5. And there we go. So make sure that you're able to do that. Go back and practice on it if you need to. Let's move on to doing some practice problems. So, I believe this is problem 2. Find the coordinates so that's xy of the absolute maximum of f of x if f of 2 equals 3. F prime of x is graphed. So maximum and f of x goes with the increasing decreasing line. We have a graph of f prime, so let's go back to our graph mode. This is f prime of x, and now remember I'm doing my translations based on this. I've got f prime, that's going to be plus minus when f of x is increasing decreasing. So fill in the plus minus line from the graph. Oh, let's see. Looks like we stop at -5 and +5. So we've got positive up until -2, negative up until 2, and positive up until 5. So when we translate that, positive becomes increasing, negative becomes decreasing, positive becomes increasing. Possible absolute maxima, it could occur either right here at the relative maxima or right here. The little circles are the possible maxima. So to figure out which is actually it, let's see, that was -2, that was 2, -2. So there are possible absolute maximum at x equals 2 and x equals 5. We want to compare them. So let's find f of -2. And remember, we have this graph here. We know what f of 2 is. So just like we were doing earlier, we want to set up, using the first fundamental theorem of calculus, a little integral that will let us calculate that. So we know the integral from -2, that's the smaller number we want to know, to 2, which is a larger number, which is what we do know, of f prime of x dx. That's going to equal f of 2 minus f of -2. F of 2 we know is 3. We want to know f of -2. And now we need to find this area right here. So from -2 to 2, this is 1, 2, 3, 4 base times height divided by 2. Oh, that was +4 here, -2 here. But in any case, it is a negative signed area. It's under the x-axis, and it is -4. So this is coming down. Draw it really lightly in pencil. Right there. So add f of -2 to both sides. Add 4 to both sides. F of -2 is 7. Now let's look at, so that was for f of -2. Now let's look at for f of 5. Well, from 2 to 5, this area, the base is 1, 2, 3 times the height is 2 divided by 3. Divided by 2. That would give us 3. So we know the area under the curve from 2 to 5 of f prime of x dx, that's going to equal f of 5 minus f of 2. We just found this area is 3. Again, that's coming from the graph. F of 5 we want to know. F of 2 is 3. So add 3 to both sides. F of 5 equals 6. We're looking for possible absolute maximum. This is bigger. F of x has an absolute maximum. At the point, because it's asking for the coordinates, the xy coordinates right here, -2, 7. Because f of -2 is greater than f of 5, and all other values are less than these. Our final problem is a check for understanding, so please copy this down, solve it on your own, and then restart the video when you're ready. It says to find the coordinates of the absolute minimum of f of x is if f of 0 equals 1. F prime of x is graphed right here. Pause the video now. Okay, f of x, absolute minimum, that's increasing, decreasing. So we've got a graph of f prime of x, so that translates to positive, negative. And let's see, it starts at 0, it ends at 6, starts at 0, ends at 6. And we can just fill in this f prime of x, positive, negative, directly. So it's positive until x equals 2, then it's negative until x equals 4 and then positive again. So translating to increasing, decreasing. It's right like that. Absolute minimum, so we're interested in this point right here and this point right here. Those are potential absolute minima. So let's start off with finding f of 0. Well, actually, f of 0 equals 1. That was pretty simple, given in the problem. Let's then go ahead and find f of 4. So we know f of 0, we want to find f of 4. So the integral from 0 to 4 of f prime of x dx is going to equal f of 4 minus f of 0. So from 0 to 4, we know that this area right here is 4. Count those little blocks, 2 times 2. We know that this area right here is going to be width of 2 times negative 3 divided by 2, so that's negative 3. And then we stop there. So the area here is 4 minus 3 equals f of 4, which we want to know, minus 0, which is 1. 4 minus 3 is 1. Add 1 to both sides. F of 4 equals 2. So this is larger. Oh, but we're looking for the absolute minimum, so we don't want the larger one. This is smaller. So that means f of x has an absolute minimum at the point 0, 1, because f of 0 is less than f of 4, and all other values are larger than these two. That concludes these notes.